You know, as a kid, I lived in quite an urban area, so the wonderful spattering of stars others got to see were somewhat foreign to me. But when I did get to see them, oh, how beautiful they were. I would gaze at the night sky on long drives through Wales and just marvel at them. But to say I saw no stars at home would be wrong. Up above, a handful of stars remained my company, and one is Polaris, the great North Star. When I was a scout, we would wander through the farmlands of the English countryside, and I remember quite clearly stopping in the middle of a field as our instructor pointed up above, showing us how to find Polaris, how to, even in the darkest nights, know where to go. I did almost die that night for unrelated horse shenanigans, but those two things have always stuck with me. The North Star and horses. From then on, when walking home on cold winter nights, I would spend a little moment looking up at Polaris under the orange glow of streetlights and find comfort in the star. For millennia, the people who have come before me have also looked up at Polaris and used it to know where they needed to go. I mean, whoa, I'm a spooky ancient ghost from another reality. Was an English physics undergrad. Whoa, ghost sounds. Well, that's enough remembering. Let's get on to discussing this star. Or, well, stars. But first, let's talk about Polaris' significance for navigation. As I have said, Polaris is often called the North Star, and for a good reason. See, Polaris lays at approximately 1.5 degrees off the exact north pole of the Earth, measuring for the more stable axis of rotation, rather than the magnetically defined north, which tends to roam a bit. This means that throughout the year, the star is approximate to the true north. This is obviously very useful if, say, you need to orient a map, as it is simple as spotting the star and rotating your map to align with it. And finding that star being very easy to do, as it's the 50th brightest star in the night sky. But accounting for it always being visible every night in the northern hemisphere, ignoring factors like cloud cover, and the bulk of stars lay in the southern hemisphere, it's hard to miss. Plus, if you can spot the Big Dipper, or Plough, constellation, then you can use the pointer stars of Deb and Merak, both also very bright stars, to carve a straight line directly to Polaris. Additionally, if you're up for a spot of maths, you can use the horizon and the angle from it to Polaris to tell you the exact latitude, within a bit of error, as long as you've accounted for refraction and any other slight inaccuracies. If you want your longitude, good luck. Now, in the modern age of GPS maps and the like, this seems somewhat insignificant. But for the last 1,000 years, this has provided incredibly useful for humanity. Well, humanity in the Northern Hemisphere, as you can't see the North Star in the south. But you guys get your own star, Polaris Australis. An awesome name. But it is beaten by its other name, Sigma Octantis. Sigma Octantis isn't as powerful as Polaris, mainly due to it being dimmer than its northern equivalent, but it is still useful nonetheless. As I have been subtly alluding to, Polaris has only been used with the North Star for a millennia or so, as the Earth does not smoothly rotate about its axis. Instead, the angle of this axis slowly rotates over about 26,000 years, leading to which star lays at direct north, also changing. Still, to this day, Polaris is slowly moving closer and closer to true north, reaching its nearest approach in around 2100, having already shifted approximately 2 degrees closer since it was given the name Pole Star, or Stella Polaris, as it was coined in Neo-Latin by Geoffricius, a Dutch astronomer, in 1547. But prior to this, been referred to similarly by the Old English as Skip Stora, or Ship Star, in modern English, due to its use in navigation by, well, ships. Or perhaps the T rune alludes to it, but both of these are speculative, and the T rune has other significant theories, such as it being an allusion to Mars instead of Polaris. In the ancient past of 3000 BC, the star Thuban was instead close directly north, reaching as close as 0.1 degree off true north. While it's hard to prove for certain if it was ever used as a North Star, there is speculation that it and Tendraconis were used by the ancient Egyptians to measure out the North Pole, as between the two, in order to construct pyramids aligned to true north. But there are other plausible theories for how they accomplished this feat, and none of those plausible theories are aliens. Unless... Then we have a period beginning by the first millennia BC, with no strong North Star contenders. Kochab is bright and closest for a while, but was a great enough distance for astronomers such as Pytheas of Mycale in 320 BC to describe the pole as devoid of stars. Then Polaris gradually became the North Star, but from 2100 till about 4200, Eri will become the new North Star, having passed Polaris in proximity by 3000 AD, more or less. And on from there it will shift, star after star, till in 26,000 years Polaris will return to be the North Star again. Accounting for a few factors, but it's less poetic. Now, the twist. Polaris isn't a star. It's a solar system of 3 stars. A trinary system of Polaris AA, AB, and B. From the names of those 3 stars, the story seems to naturally unfold. Originally, since time immemorial, people would see Polaris, if under different names, as a single star. But in 1779, famed astronomer William Herschel discovered that a second star could be resolved from Polaris with his more modern equipment. This new partner star was of course designated Polaris B, with the brighter original Polaris remaining being referred to as Polaris or as Polaris A, depending on the convenience of the discussion. Then in 1899, William Wallace Campbell then observed that Polaris A seemed to have a steady repeating pattern, modifying its velocity, as if it was orbiting a body incredibly close to itself. And with how massive Polaris A was, this would have to be another star. In the following years and decades, this belief was reaffirmed by further investigations, such as Joseph Haynes Moore's work in 1927, which proved that the observed effect was a combination of a 30-year orbital period with this other smaller star and the larger star's Cepheid cycle, which will be elaborated on soon. This Polaris AB proved difficult to observe directly due to the sheer size of Polaris AA and its closeness. But in early August 2006, the Hubble Space Telescope at long last had the power to resolve the two bodies, meaning all three stars had been finally imaged. Let's get into some data. Polaris AA is the best place to start. It sits at solar masses and 46.27 plus or minus 0.42 solar radii, with a temperature of 6015 Kelvin and a bolometric luminosity of 1260 solar luminosities, making it a yellow supergiant. To give a bit of clarity on the last two qualities, a bolometric luminosity is not how bright a star is in the sky, that's being its radiant flux. It is instead the total amount of energy it emits that is its luminosity, and it being bolometric just clarifies that it is the entire electromagnetic spectrum which is being read, not just the visible light. So things like gamma rays and radio waves and everything in between are all counted. Now, temperature in this context is the temperature of a perfect black body that would have the same emittance. I would elaborate further, but we are already looking to be overrunning. So expect a black body radiation explanation in an entry on a less interesting star. Next is closest satellite. Its proximity making extracting information on it difficult. Polaris AB. It orbits with a period of 29.416 plus or minus 0.0028 Earth years, and has a mass of 1.316 solar masses and a radius of 1.38 solar radii. Although sources disagree, so this should be taken as ballpark values. This makes it a main sequence star comparable to your own sun, but it is hotter with a temperature of a ballpark of 6400 Kelvin, of course, and a bolometric luminosity then of around 3 solar luminosities. Then finally, Polaris B. It lays about 2,400 astronomical units from the star's combined centre of mass, and it completes an orbit roughly every 40,000 years. Taking the human Neolithic revolution as a starting point of your society, in all that time, Polaris B has just barely made it round a quarter of its orbit. And since you first evolved into Homo sapiens, Polaris B has only orbited Polaris A 7.5 times. It comes in at a mass of around 1.35 solar masses and a radius of 1.38 solar radii, with bolometric luminosity of 3.868 solar luminosities and a temperature of 69,000 Kelvin. That's quite hot. Oh, I'm keeping that in. Making it another main sequence star, larger than your sun and a little bit hotter. Now, I have a puzzle for you. How do you measure how far away a star is? First instinct is to measure it against something. It's natural to do so. It's how we do most of our distant measurement in day-to-day life. Use a reference points in your environment to compare, but how do you do that with a star? Well, I guess we could have a standard distance to use to compare, but how do we find this standard distance? The stars are so distant and with such voids in between that none appear naturally. But we can be clever. We understand how light works, how it dissipates as an inverse square of the distance. But now we need a standard light source, or a standard candle. But then, how do we measure how much light a body emits? The only thing we can measure is what reaches us here on Earth. So, after the dissipation has occurred, which means distinguishing the star as being brighter or just closer, seems at first impossible, but wonder no longer, for the wonderful Henrietta Swan Leavitt has given us a way. See, despite having grown deaf due to an unknown condition, she worked tirelessly and discovered that a class of stars known for going from day to week-long pulsations, called Cepheid variables after Delta Cephei, the second one to be discovered, could have their flux measured against the logarithm of their pulsation period to find a straight line, which means a parallel relation. And that means we can figure out what luminosity a star is just from how quickly it passes through its Cepheid cycle. This was, at last, the standard candle that scientists had been searching for. It was groundbreaking. Now, if humanity could calibrate this spectrum, every Cepheid would become a standard candle, and that could be used to calculate a standard distance, and we could use it to compare its neighbours. Soon, the astronomical community rushed to measure as many Cepheids as possible, using a method called parallax, which utilises trigonometry and the different angles stars appear to be at during different parts of the year, as you orbit the Sun, to measure the distances to these Cepheids as precisely as possible, to as tightly measure Leavitt's law. It is not an understatement to say that all of modern astronomy rests on Leavitt's law. Now, what does this have to do with Polaris? Well, as I said before, Polaris A is one such Cepheid variable. And not just that, it's the closest known Cepheid variable. So, studying Polaris A's distance is very crucial in further increasing the accuracy of Leavitt's law, and by extension the entire distance ladder, which relies on our measurements of distance at short scales. Several surveys have disagreements on the exact distance to Polaris, but the latest by Gaia DR3 places Polaris at 446.5 light years away, with an error of about 1.1 light years. And in December, we expect Gaia DR4 to give an even more precise measurement of it, and numerous other Cepheid distances, so Polaris is still guiding us to this day, if not on ships, but in space instead. Turns out, when you look into a body that isn't some random rock, there's a lot more to say, huh? Well, what stars the Polarises are, and what insights they give. And to think of how many other interesting stars and rocks there are with wisdom to bestow on us. Well, that's enough for today. I've talked your ear off, I assume. But if not exhausted by my yappage, why not like and subscribe? And hey, comment what you want me to talk about next. Unfortunately, it will be a random rock. You cannot stop that. But what's after that? Who's to say? It's up to you to decide. Oh, and if you didn't know, I do some streaming on Twitch from now and again. It's not formal education stuff, and it's just me relaxing and having a good time. But that's enough self-promotion. Good night, and see you soon.